Throughout AP Physics 1 and AP Physics 2, we've been talking about exclusively classical physics. That includes classical mechanics, that goes all the way back to Newton and Newton's laws, as well as classical electromagnetism, so that's electric fields, magnetic fields, all these things that James Clerk Maxwell linked together in the 1860s. Now, the thing is, though, is that that was not the end of the story for physics. And in fact, about 30 to 40 years later, in about 1890 to 1900, we started to notice a bunch of different things that were not adding up quite the way they should. And that became the basis for what we now know as modern physics, which really started to emerge around 1900. Now, modern physics can be grouped in a bunch of different ways, but we're going to be looking exclusively in this unit at quantum physics, atomic physics, which are very closely linked, and nuclear physics. So we're going to start with quantum and atomic. The second half of the unit we'll start talking about nuclear. And today's lesson is going to be focused on this very pivotal experiment, and frankly unexpectedly pivotal experiment, known as the photoelectric effect experiment. Now, when the photoelectric effect was first discovered in 1887, it was kind of seen as being a bit quaint and trivial and something that maybe we would look into, but really nothing that important. So what does this experiment consist of? Well, we have a phototube, and this phototube is a evacuated glass tube. In other words, a tube with all the gas pulled out of it. And we have in here two pieces of metal on each end of the tube, and they are connected by a wire to each other, and we have an ammeter connected here. So this is kind of like a parallel plate capacitor, but since there's no voltage source, okay, well, we would expect there to be, no current. And additionally, what we have is we have a light source that we can vary the intensity or the brightness of it, as well as the frequency or the color of light from it, and we're going to shine this light on this cathode here. And this cathode is just the name for this particular piece of metal. And when we do that, well, all of a sudden, a current starts flowing through this wire. Okay, well, how exactly is that possible? Because, to have that happen, we must have a closed circuit, which means electrons must be going from the cathode, or the electron donator, to the anode, the electron collector or acceptor, somehow. But how exactly is this happening? Well, typically speaking, when we talk about electrons escaping a material and therefore jumping this gap, we think about, okay, well, maybe we heat them up. And if we heat them up, they're going to start vibrating more and more and more and more and more, gaining more and more thermal energy until eventually they fly off and escape. And perhaps that's what's happening here, is that when the light is hitting the metal, it's causing the metal to heat up, and that's causing the electrons to jump across. And that was basically what was thought to be the idea. But this is essentially this phenomenon is what is known as the photoelectric effect. Photo just essentially meaning light, and electric referring to the electrons in this generation of an electric current. So the photoelectric effect is the emission or the ejection of electrons from a metal when light strikes it. So they're being ejected from the cathode, and then they're going to the anode. And they're actually going in a bunch of different random directions, but we're just going to focus on the ones that make this direct path. So in the late 1880s and early 1890s, we started studying this photoelectric effect. And we started thinking, okay, what are different things we can do to kind of change what's happening here? So first off, how can we increase the number of ejected electrons from the metal? And by doing so, we're going to be increasing the current through the wire. So if you have more electrons going through the wire, that current's going to go up. Alright, so what exactly do we predict is going to happen? Well, usually what we would think is, okay, well, maybe if we increase the brightness of the light hitting the metal, that's going to increase, the amplitude increases the energy. And if we increase the energy, well, then we're going to have more energy available to more electrons. And okay, that makes sense, then maybe we would get more electrons generated in this way. Now, if we change the color of the light, well, that really shouldn't do much of anything. I mean, yeah, we're going to have a higher frequency, but that's not going to change how many electrons can get really hit by this. Additionally, for a dimmer light, we would expect that maybe it will take more time for the electrons to be emitted than for a brighter light. Because if we hit it with a dim light, the electrons might start to oscillate, but we're going to have to keep hitting it with more and more and more, so they gain more and more and more and more energy until eventually they build up enough and maybe they can fly off. So let's go ahead and see what exactly we observe and see if they match these predictions. So let's go back to the setup here, and let's go ahead and start with violet light that is pretty dim. So this is a very high frequency, but a pretty low intensity. And when we do this, we see that a current does indeed start to form, but it's relatively low. So we have very few electrons jumping this gap. Well, if we turn up the brightness of this violet light a bit, it's going to be a little bit brighter, and we see that the current increases. So therefore we have more electrons jumping the gap, and if we increase it even more, if we make it as bright as we can make this violet light, even more electrons jump the gap, we get an even bigger current. So we get this nice linear trend that as we increase the brightness of the light, the current does indeed increase, meaning that more electrons are jumping the gap. But are we positive that that's true for every color of light? So let's change up the situation a bit. I'm going to just go ahead and make this now a yellow light that is fairly dim, and we get a fairly low number of electrons being ejected. It's low current. And if we increase the brightness of that yellow light, well, a lot more electrons get ejected and we get a much higher current. So this tracks. And let's keep checking. So now let's go ahead and say we use an orange light. So that's a lower frequency than even yellow light. And if we do that, well, we still get a current. And if we turn up the brightness even more, we get an even higher current. So more electrons are being ejected. Once again, this tracks. But just for completion's sake, let's go ahead and shine a red light on this cathode. And a red light is about the lowest frequency we can get of visible light. So this will be the lowest one we can see. And when we do that, well, it's dim, granted, but we're not getting any current here, meaning that no electrons are being ejected. But, let's give it some time. Well, we're giving it time, and even though we're giving it time, we expect maybe the electrons are building up their energy. Still nothing's happening. So you know what? Let's speed up the process a bit. Let's go ahead and turn up the brightness of the light. But when we do that, we still don't get any electrons being ejected. In fact, the current has stayed zero the whole time. So these are the predictions that we made. And did what we observe match these predictions? Well, kind of and kind of not. First off, we did indeed see that if we increased the brightness or the intensity of the light source, that increased the number of electrons being ejected and therefore increased the current in the circuit. But while this was true for all the different frequencies of light we saw, for orange, yellow, violet, it wasn't true for red, telling us that there's some threshold frequency, and if we're beneath that frequency, for some reason, no electrons are being ejected, no matter how long we wait. And in fact, this is one other point that we had wrong. The brightness or the dimness didn't really matter. If it was dim, they pretty much ejected electrons immediately. If it was bright, pretty much ejected electrons immediately, unless we were beneath that threshold frequency. If we were beneath that frequency, it didn't matter how bright we made it, didn't matter how long we waited, no electrons were ejected at all. And this goes counter to what we were expecting. Well, while we were looking at the number of electrons being ejected, is there some way we could study the energy of these electrons? Well, the energy that the electrons gain must be coming from the light. That must be where it's gained from. So the energy of this electrons is equal to the energy of the light. And what is this energy equal to? Well, it's equal to the kinetic energy of the electrons, granted. So if it's given more energy, they're going to have more kinetic energy. They're going to be moving faster. But additionally, they had to have some energy to even escape from the metal. And this right here, this is a Greek letter phi, P-H-I. And this stands for what is known as the work function. Now, that's a very archaic term. All that really is telling you, work function, when you see that phrase, is that's the amount of energy necessary to eject an electron. The amount of energy necessary to overcome its attraction to all the nuclei in the metal. If we get that much energy, it can leave. And then if we have extra energy, it goes to the kinetic energy of this electron. Now, the thing is, though, is that how could we investigate this extra energy? Well, let's go ahead and hook up here an adjustable voltage source. I've hooked this up now, and I've got a positive side on the cathode and a negative side on the anode. So electrons are attracted to the cathode and rejected or repelled from the anode. So basically, we're charging up these plates. And I'm going to go ahead and say that I've turned the voltage source up a little bit, so I get a little bit of negative charge over here, a little bit of positive charge over here. And what that's going to do is some of the electrons, if they have enough kinetic energy, they're going to leave and they're going to make it all the way across anyway, and we're going to detect that with the current. But some of these electrons, if they have less kinetic energy, well, they're going to start going this way, but they're going to slow down, they're going to be repelled from this, and they're going to start accelerating backward, and they're going to go back to the cathode and not add to the current in the circuit. And in fact, if I want to know what is the maximum kinetic energy of any of these electrons, well, I need to keep turning up this voltage source until none of them can make it across from the cathode to the anode anymore. And this is something known as the stopping, let's make this a little easier to see, known as the stopping potential. So the stopping potential is the voltage required to stop all electrons from reaching the anode. They're still ejected from the cathode, but now that they're repelled, they start to go back the other way. Now, how can we figure out how much kinetic energy these have? Well, if it's just enough to stop them from making this gap, well, the kinetic energy that they are losing as they're going here is being stored as electric potential energy in the field generated by these two plates. And we can calculate that by the charge of an electron times the voltage between the two plates. So if I want to know how much kinetic energy these have, I can say, all right, well, how much electric potential energy do they gain, because that's how much kinetic energy they lost, and that will be equal to the charge of the electron, so 1.6 times 10 to the negative 19 coulombs, times the stopping potential, whatever exactly that voltage is that causes this current to stop and go to zero. So while we've talked about the number of electrons increasing in the photoelectric effect, how can we increase the amount of energy they have when they're ejected? Which basically how we can determine that is what's going to affect how much we have to turn up that stopping potential. If the stopping potential is higher, that means we have to put in more energy to cause the electrons to slow down, stop, and turn around. So the higher that is, the more energy they have. Well, once again, we would expect it to be related to the amplitude of the light waves, because the amplitude, or that brightness, is related to the energy of the wave. So if you have brighter, we would expect there to be more energy if we turn that brightness up. Additionally, once again, we wouldn't expect there to be any difference for the different frequencies. In other words, if we have red, orange, yellow, purple, blue, green, whatever light, that shouldn't affect how much we have to turn that stopping potential up or down. So once again, here's our setup. We now have the adjustable voltage source connected in with a little voltmeter on it. And let's go ahead and once again start with some violet light. So I'm going to turn the violet light on. It's going to be relatively dim. And so we have a few electrons being emitted, and they all have a pretty good deal of kinetic energy here. This stopping voltage is pretty darn high. They are moving pretty darn fast. So if I look at this here, I've got my graph of the brightness versus the stopping potential, and I have this data point here. So let's turn up the brightness of this violet light. Well, when we do that, we get more electrons, so the current would be going up if we didn't have the stopping voltage here, but that stopping voltage value doesn't change. The electrons seem to have the same amount of energy, even though we've turned that brightness up. And in fact, if we turn it up even more, well, that stopping potential has stayed constant the whole time. In fact, it appears that the brightness doesn't affect the amount of energy the electrons have at all. But maybe that's just a quirk with violet light. So let's go ahead and change the frequency a bit. Let's go to some yellow light. And when we do that, okay, we've got that going. We've got a pretty medium stopping voltage here. And if we turn the brightness up, well, nope, it also stays constant. Doesn't seem to have any effect. And let's go ahead and try orange too. All right, so I'm going to turn it up. All right, we've got a few electrons, and, they've got a pretty low stopping voltage here, so maybe it'll increase if I turn it up, but nope, it also stays constant for this brightness. And lastly, okay, what about red light? So red light, remember, has a really low frequency, but we already noticed previously that we couldn't even get any electrons to come from there at all. So the stopping voltage is just zero, because the electrons have literally not left. They don't have any kinetic energy escaping from here. No matter how much I turn up the brightness, it's always going to stay at a stopping potential of just 0 volts. So once again, this was our prediction, and unfortunately, this prediction was pretty much 100% wrong. One, it appears that changing the brightness doesn't increase the energy of the electrons. Instead, we need to increase the frequency. In fact, if you noticed, if we looked there, the violet values were pretty high for stopping voltage. Then it was yellow, then orange, and red was 0. And so the frequency actually affects how much stopping potential we need, and therefore how much energy these electrons have. Up to a certain point. Remember, beneath this point, if we're below this threshold frequency, no electrons are ejected at all, so the kinetic energy is just 0. So this is the plot we would see here. Additionally, we saw that the energies didn't change no matter how much we turned up the brightness. Dim light, bright light, we got the same stopping voltage and therefore the same energy electrons every single time, as long as we kept the frequency, or in other words, the color of light, the same. So what exactly is going on here? Because we've been doing all of these things and following how light behaves like a wave. You know, that light has energies that are proportional to its amplitude, to its brightness, but that doesn't seem to be working properly in this context. And this is where the confusion came from for about 15 years or so, until about 1905, when a new idea was brought really to the fore. And that was the quantum, otherwise known as the particle model of light. So this quantum or particle model tells us that light, or electromagnetic radiation, is in fact quantized. And by quantized, we mean that it moves in indivisible chunks, otherwise known as quanta, or if we have a single chunk, a singular chunk is called a quantum. So it's a quantum. If we have multiple chunks, they're called quanta. So in other words, light exists in these little indivisible packets of electromagnetic energy. And this was an idea that was first introduced by Max Planck in really before 1905. But Max Planck, who was a German physicist, really just came up with this idea as using them as a useful trick. Basically, if he treated light in this way, he could solve some problems that we're going to talk about more in class. But then in 1905, Albert Einstein saw this trick that Max Planck had used, and he was like, that's not just a trick. That's actually how light behaves. It actually describes reality, and it explains the photoelectric effect. And this particle model of light you're actually familiar with, even though you don't realize it, because light quanta, these light chunks, are known as photons. So a photon is a quantum of light energy. It's a particle of light energy, or a quantum of what is known as the electromagnetic field. It is a fundamental particle that is indivisible. It cannot be divided into different pieces. It has to exist in the singular form. So we can have multiple photons. We can have an integer number of them. We can have 1 photon, 2 photon, 3 photon, 4 photon, etc. But you can't have half photon. You can't have a third of a photon. They always exist in these chunks. And they can only be absorbed in their entirety. Now, what I mean by that is if I have an electron and a photon comes in, it takes in the entire photon. It can't just take half, because photons can't exist in those fractional amounts. Now, when we say that, this amount of light energy, well, how much energy does the photon carry? Well, it carries an amount of energy related to its frequency. Seen in this equation here, capital E is equal to HF, where E is the energy of a single photon of a specific frequency. So not every photon has the same amount of energy, not every individual photon. It depends on the frequency of light that it comes from. Purple photons or violet photons will have more energy than yellow photons, which will have more energy than red photons, but they still exist in these singular packets. The frequency F is in hertz, and H right here is known as Planck's constant. And Planck's constant has a couple of different ways of formulating it. We have 6.63 times 10 to the negative 34 joule seconds if we want the energy in joules, or 4.14 times 10 to the negative 15 electron volt seconds if we want the energy in electron volts. Typically, we want it in joules if we're going to do any sort of calculations, but electron volts are oftentimes a lot easier, and so we'll use that one a lot too. Additionally, just a quick note, photons are these massless particles of energy, and they travel at the speed of light. They are literally what light is composed out of. So how exactly does having light act like particles or photons explain the photoelectric effect? Well, let's first look at this violet light. This is a dim violet light. We've got a few electrons ejected. They have pretty high energy. Well, the thing is, though, is that since it's a high-frequency light, since this frequency of light is violet, that is very, very high-energy photons. We have these particles of violet light coming in, and they strike the metal plate, and electrons absorb them in their entirety, meaning one electron gains a lot of energy. It gains that entire packet of energy, and that's enough energy for it to, 1, escape the metal to overcome what is known as the work function, and 2, to gain a lot of kinetic energy. Whatever is left over after it's escaped the metal is now belongs to the electron as kinetic energy. It's allowing it to move through space faster. And if we turn up the brightness of the light, well, we get more photons coming in. And if we have more photons coming in, that means more electrons can absorb them. It means more electrons can escape, and we increase the number. But the energies of the electrons don't change because they each have just absorbed one single photon of violet light. Well, what happens if instead we have the yellow light? Well, once again, we have a dim yellow light here, so that's going to be a few yellow photons, and yellow has a lower frequency than violet, so these photons have a lower amount of energy than the violet photons, meaning that the electrons that absorb them, well, they have less energy. They're going to be able to overcome the work function still, but they're going to have less extra energy, so they have less kinetic energy. They're not moving through space as quickly after these individual photons have been absorbed. But once again, if we add more photons, that means more electrons can absorb those and more of them will escape. They're still, though, going to have that smaller amount of kinetic energy. Well, what about the red light? Remember, the red light wasn't allowing any electrons to be ejected at all, and that's because these photons are below what is known as the threshold frequency. These are even lower energy photons, and in fact, these are such low energy that the electrons do absorb them, but it's not enough for them to overcome the work function. They can't escape the metal, and since they only accept one of those electrons, they just can't get away, because they don't have enough energy to therefore escape and move outward from that point. Now, you might be thinking, well, if we add more photons to them, doesn't that mean an electron could absorb multiple photons? And the thing is, though, that's not really how it works, because electrons, statistically speaking, are only going to be absorbing one photon at a time. They actually release photons pretty quickly afterward. We'll learn more about that later. So once they absorb one photon, they gain that energy, they're going to quickly lose it, and then they might absorb another photon, but they're not going to absorb two at once. So no matter how many photons we give them, they're not going to be able to overcome the work function, they're not going to be able to escape this metal. So we don't see any electrons being ejected, no matter how much we turn up the brightness. So one final point to remember. So, okay, the energy of a photon that's absorbed will equal the energy of the electron, the energy that that electron has gained. But the thing is we now know that the photon energy is equal to Planck's constant times the frequency, and we know the energy of the electron is going to be the work function, how much it absorbs to get out of the metal, and then whatever additional kinetic energy it has. So if we want to, we can reformulate this equation, and we often see this written as K max is equal to HF minus phi. In other words, we have the photon energy minus the work function, whatever's left goes to the kinetic energy of the electron. And a lot of times we'll see this plotted on a graph like this. So this graph here shows me the kinetic energy of the electrons in either joules or electron volts, depending. And on my x-axis, I have the frequency in hertz. And we know that if we increase the frequency more and more and more and more, that we're going to have more and more and more kinetic energy. And additionally, looking at this here, I could rewrite this as y is equal to mx plus b. This is my y-coordinate, f is my x-coordinate. So if I plot this, I'm going to get a straight line where h is the slope of this straight line. So Planck's constant would be the slope. And the y-intercept, which notice is negative here, will be the work function. So if I find this y-intercept, that tells me how much energy an electron needs to absorb to escape the metal. Okay, so I've got that here. But the thing is, though, is that, this is kind of misleading because we can't have negative kinetic energies. So we might need to accept this much energy, but this isn't really accurate. I actually need to really redraw it like so. That basically they have no kinetic energy until we reach this point here. And this point here is known as the threshold frequency, and then we can start getting higher and higher kinetic energy. What is this threshold frequency? Well, that occurs when the kinetic energy of the electrons is zero, when we have just enough energy to get them to escape the metal. So therefore, our work function will just be equal to the energy of the photon, hf, but we're going to say specifically f naught, where f naught is that threshold frequency, the minimum frequency of light we need a single photon of to get an electron to escape. If we have anything below that, the electrons are not getting out. So this is like, for instance, yellow light. If we have photons of red and orange energy, no matter how much we provide, the electrons are not getting any kinetic energy out of that. They only get it if we go higher in frequency than that threshold frequency. One last thing I want to note here is that this particular work function is for a specific metal. If I have a different metal, it's going to hold on to its electrons a little differently and might require more energy or less energy for them to escape. And so we're going to see the same sort of graph shape, but it's going to be shifted a little bit to the right or left. So it's going to have a different threshold frequency necessary to get it off, but it's still going to have the same general shape of the slope of being Planck's constant and the y-intercept being the work function. Okay, so what are the big takeaways talking about the photoelectric effect? Well, one, can we describe what the photoelectric effect is in the experiment? And can we really talk about specifically what are the trends we observe? Can we explain these trends using the photon, otherwise known as the particle model or the quantum model of light? And can we analyze situations involving the photoelectric effect specifically for factors such as the threshold frequency, the kinetic energy of the electrons, work function, etc.?